So there are four computational classes: P, NP, NP complete, and NP hub. Whatever problem you will face, you will solve, or you will formulate, or you will encounter in your life, your problem will be any one of these class. So if your problem comes in the class P, then we don't worry for that problem because we have the solution that we can solve that problem in reasonable time. But if your problem belongs to NP or NP complete or NP hard, then they are difficult problems. So in fact, if you have the problem, if your problem comes in the NP or NP complete or NP hard, then you will not have the algorithm that can terminate in reasonable time. Your algorithm will take much time, and it may be busy with computation. It may go to the infinite loop. And the problems which are in the NP hard group, even you may not have any algorithm of any time complexity. So before solving the problem, actually, we should know that what is the characteristic of the problem, means in which class your problem comes. If your problem comes in the class P, then you will have the solution, just like we have the solution for the searching, sorting, matrix multiplication. These are the problems which comes in the class P. So for all such problems, we have the polynomial time algorithm, means the algorithm runs in the polynomial time. You have some sort of analysis where d is some exponent and n is the number input size. So d generally we consider that d should be 3, and if d is more than 3, means degree becomes more than 3, then you also take much time. So truly polynomial, if you solve in the reasonable time, then you should have degree order of n cube. It will be it will be okay. And most of the problem we have seen, even the all pair shortest path problem, or you have matrix multiplication problem, you come to know that the complexity of such problem is n cube. We have the sorting problem, which is the n square was some problems, and n log n in some cases. Searching algorithm takes log n time for some binary search, and linear search takes, you know, that order of n time. So all such algorithms have the polynomial time analysis. So that's why the such algorithm comes to the class P. We say that these are in the class P problem. So once your problem is belongs to the class P, then we have the algorithm that runs in the deterministic polynomial time. And see, whatever algorithms we have seen yet, every statement of your algorithm you can implement in your programming language. Means every statement has deterministic, you don't have any such choices. But see, if you consider some algorithm for searching in different manners, okay, if you consider the searching algorithm, so in case of the searching algorithm, what we need, we have some value x, we need to search, we need to find out whether this element x is in the list or not. And you are given the list A, you may have the 1 to n elements in the list, and you want to find out the position of this element in this list. So this is the simple problem of searching. So if you go for the binary search algorithm, then you know that order of log n time is needed. And if you go for the linear search, then order of n time is needed. So see, order of n time for the sequential search or linear search, you come to know that. And in that case, these algorithms are deterministic in nature. Every statement of the algorithm has clear and unambiguous meaning. So statement of your algorithm is clear and unambiguous. So that's why whatever algorithm we have uh, write, or we have seen for the searching, sorting, or matrix multiplication, they are the deterministic algorithm because every statement is clear and definite. Here, if you write in the different manner, like, see, if you have some, say for example, if you have some statement available like choice, you have the choice. And you can, somebody can say that choice 1 to n, you have n elements in this list starting from the 1. We assume that it is starting from the 1 to n, we have the list. So you have 1 to n element, so your index can be either 1. Once you find the location of x, then it can be either 1 or it can be either n or it can be anything, 2, 3, 4, 5, 6. And if item is not present, then some we can say that okay, your algorithm will return some zero index. Once you find the zero index, because you know that your elements are starting from 1 to n, and if your algorithm is going to, what is the output of this algorithm, whenever you write some algorithm, every algorithm has some input and output. So here the input is the list, and the element you want to search, and output is the index from 1 to n if element is in the list. And if element is not in the list, then your algorithm will return the value 0. This is the searching algorithm. So if we have this kind of statement, choice 1 to n, and we have some, say for example j, and j is the integer. So you have j, and we can assign this choice 1 to n. What we assume that the choice 1 to n, this is the statement. We are not going to consider as the function here. This is the statement which will determine the index from 1 to n. And if x is available in this list from 1 to n position, then this function returns the index, correct index. So this is the condition we see in the choice function. So see that this choice function is identifying the value index from 1 to n. If x is in the list, then it will output the correct index, and if list item is not in the list, then it will return some garbage value like 0. So see, int j, you can write the statement like this, and then what you need, just what you assume after execution of this statement, we have the value j, which is the index of the uh, uh, list where the x is found. So now we need to find, x may be available in the list, x may not be available. If x is available in the list, then you will have the index from 1 to n. So you can just check if, what you can say, if aj, you have the aj, j is the index returned by the choice, and if this is equal to x, you wanted to find out, then what you need to do, if this is the index, then you are going to return, say for example, you in c++ or C out, you can say that like this, what you are going to return, j, and then you can say that success. Okay. Success. Otherwise, if this is not true, then what you need, you are going to return some garbage value, which is, say for example, you are going to return 0. Okay, so this is the algorithm. That's all. Now see, if you execute this algorithm in your programming language, whatever programming language is available, then what will happen? As soon as you enter choice 1 to n, your compiler will generate the error, and it will ask that okay, what is the this is the unknown identifier. Means computer has no meaning of choice. This statement is not clear. What you mean by this? As you have not defined anywhere. If you want to go for the deterministic algorithm, then you must define the choice function, how you are going to make the choice, how you are going to decide the index value. And if you go like this, then it will become the deterministic algorithm, like searching or like sequential search or binary search. So what we are going to do is, we assume that computer is intelligent enough, and it will take decision. It is going to take decision out of the n indexes. It will pick up the index where the item is found. If item is available in the list, then it is guaranteed that this choice function will return the correct index. Otherwise, it will return some garbage value like 0. So Okay, this is the condition, and we are not going to write the choice function anywhere. So if you go for the implementation of this algorithm, you will not find any programming language where you can implement this statement, because your programming language is deterministic in nature. What and this choice function will return the value in the constant time. This is the assumption we are going to make. The statement, this statement has constant time, means if n is 100, then also it will take the decision in the same time, and if n is 1 lakh, then also it will take the decision in same. If 1 micro millisecond is needed to make the decision from 1 to n for 100 elements, then it will, the 1 millisecond is also needed for 1 lakh or 1 billion and whatever. So that's why it is independent of the value of n, and this statement has constant time. This is the assumption. And if the item is present, then this will be same, this will be true, and you are returning the index value, and you are signaling the successful termination. So the success is the function which is also run in the constant time, and this signals the successful termination. Otherwise, what you need to do, if this is not true, then you can output the 0, and then failure, you can signal the failure. And this is the function which takes the constant time and which signals the failure termination. So this is the cases. Now see, if you go for the analysis of this algorithm, then this is the constant time. We have assumed that choice will take constant time, and you know that this is also constant time, this is also constant time, success has also constant time, this can also be done in constant time, and this is also the constant. So overall complexity of this algorithm is constant. So in you are able to determine whether the element is present in the list or not in the constant time. But this is the algorithm where the statement you have made choice, and you have not defined any function, explicit function, how you are going to make the choice, and hence this is not the deterministic algorithm. So this is the non-deterministic complexity. So you can say that this is non-deterministic complexity. So non-deterministic complexity of your searching algorithm is constant. Okay. So this algorithm, since this statement is not clear, so we can say that this is the non-deterministic algorithm. Non-deterministic. This is the non-deterministic algorithm. And non-deterministic algorithms cannot be implemented in any programming language. So why we are going to write the non-deterministic algorithm? Because we assume that if such programming language available, means if such intelligence computer is available, where we can execute this kind of statement, then many complex problem, like you have seen 0-1 knapsack problem, or satisfiability problem, queens problem, traveling salesperson problem, can be solved in the reasonable time. Because you know that if you can have the choice function which is independent of the input size, and it runs in the constant time, then whatever be the input size, you are executing the statement in constant time, and your algorithm has reasonable time to solve. Means the algorithm which, for which you have the deterministic algorithm which runs in the exponential time, can be solved in the reasonable time if you have some programming language which can execute your non-deterministic algorithm. So this is the notion of the non-deterministic algorithm. So whenever you go for the analysis of your deterministic algorithm, then we will say that okay, this is the deterministic, and the deterministic complexity of your algorithm. When you analyze your non-deterministic algorithm, then you can say that okay, this is the non-deterministic complexity. So in this way, with the help of the non-deterministic complexity, non-deterministic algorithm, actually we are going to define this group. NP here, you know that NP stands for the non-deterministic. N means non-deterministic, and here P means polynomial time. So see that if you have the class P problem, so problem will come into the class P if you have the deterministic algorithm that can solve in the polynomial time. If you have deterministic algorithm which runs in the polynomial time, then it will be in the class P problem. When you have the non-deterministic algorithm that runs in the polynomial time, like we have written, this is the non-deterministic algorithm. Since searching problem has deterministic algorithm which runs in the polynomial time, that's why then this algorithm will searching problem will come into the class P problem. But there are problems for which you don't have the deterministic algorithm which runs in the polynomial time. Like see that we have the you have seen the 0 1 knapsack problem. Okay, 0 1 knapsack problem. Knapsack. In 0 1 knapsack problem, what we have assumed that you have the n objects. You have n objects, okay, and every object has some weight of ith object, and you have the profit of ith object, and you are given some sort of capacity of your knapsack. You can hold this kind of item. And what we assume that what you are going to do, you are going to maximize the objective function, which is the pi n xi. Here I is equal to 1 to n. You have the n objects, and here the constraint is what? The constant is xi. Every xi can take the value from the set either 0 or 1. This is the constant. Means you can select or reject. This is the string. And the total weight of selection means wi should be less than or equal to the given capacity. So these two are constants. These are the constants, and you need to maximize this objective function. So see, if you are given the n objects and you want to make the decision, if you go for the algorithms, whether you can go for the dynamic programming algorithm or brute force algorithm, then see that if you have the n objects, so you have the n objects means you have to decide for every object, say for example x1, x2, x3, and you can have the n. So you can decide whether it is 0 or 1, whether it is 0 or 1, whether it is 0 or 1, whether it is 0 or 1. So if you go for the brute force algorithm, then you see that 2 raised power n, the algorithm runs in the time 2 raised power n. Okay, because you have the n values and everywhere you have the two choices. So how many possible tuples are there? 2 raised power n tuples you possible examine. So starting from 0 0 0 you need to test, then 0 0 0 1 you need to test, then all ones you need. So 2 raised power n tuples you need to examine to find out which value is going to optimize the objective functions. So this brute force algorithm, if you go for the even brute force or dynamic programming also, even you have the exponential behavior. Now, if the function like choice available, which runs in the deterministic constant time, if you can write the non-deterministic algorithm, then what you can do? You just run a for loop actually for say I is equal to 1 to n, because you have the n items, n objects, and what you need to do, you can take some, you have the x, you need to decide for the xi, and x is the list which will hold the value for the fraction x1, x2, and x3. Now if you have the choice function, choice, okay, so just like you have the choice here, and here you have the only two choices, either 0 or 1. Okay, so you have for every, when I is equal to 1, you are going to decide for the first object whether first object should be selected or not selected. So you have choice 0 or 1. And what we have assumed that your machine is intelligent one enough, and it will determine the correct value whether 0 or 1, so that your objective function will be give the optimum solution. So we believe that. So this is the way. Now you have the choices. Once you run n times, order of n times, this loop will go to order of n times, and since this is the constant time, so overall from here to here you have the order of n time you need, and order of n time is needed for finding the value of x size. Now accordingly you can determine the profit, because as per the value of xi, whenever you have the 1 you can add, whenever you have the 0 you can not add. And this is the way. So next time you need to verification. So whenever you have the choice, after the choice execution of this choice, you have got the indexes. Now you can simply run one for loop, and you can go for 1 to n and examine the value of xi. If it is 1, you can add into the profit, and also you can wait, you have the sum, you are increasing some weight. Then once you go for the next choice, then it may be xi can be 0 or 1. If it is again 1, then again add the profit, and weight you can also add in the previous one. You are going to update and see that what is the remaining weight, like this. And you can verify if this, I have told you that this choice function, we believe that this choice function will give the correct output if such possibilities is there. So this is the way. See, if you write the non-deterministic algorithm with the help of the choice function, if you write the algorithm for 0 1 knapsack problem, then it will run in the polynomial. This is the polynomial time. Here order of n time is needed. N times, because you have the n choices. X size, there are n tuples are there, and you can see the value accordingly, and you see determine the profit or loss. So see, this is the polynomial time algorithm, but this is the non-deterministic polynomial time algorithm. So you have, if you go for the deterministic algorithm, this will, then it will have the exponential time, but once you go for the non-deterministic algorithm, then you have the polynomial time. So that's why this 0 1 knapsack problem, you have the 0 1 knapsack problem, we don't have the deterministic algorithm which runs in the polynomial time. So this problem will not come in the class P, but this will come into the NP group, because we have the non-deterministic algorithm that runs in the polynomial time. So this is the n stands for the non-deterministic, P for the polynomial time. So this is the notion of the P and NP. And we have the relationship on the P and NP. So people have believed that we have the P, class P problems, and we have the NP problems. So people assume that this is the relationship available for the P and NP. So this is the NP, this is the NP, and this is the, so P, class P problems are the special case of the NP. This is, and there is a biggest question is still there. People are going to prove whether P can be equal to NP, or P is not equal to NP, or P is subset of NP. So these are the question, open question, and with our experience, people believe that P is the subset of NP. Commonly, people believe this kind of relationship, P is the subset of NP, but no one can prove that P is not equal to NP, or no one can prove that whether P is equal to NP. And there are $1 million prizes are declared those who can prove that P is equal to NP or P is not equal to NP. So people believe that till now, like we have seen that 0 1 knapsack problem. Till now, we don't have the deterministic algorithm which runs in the polynomial time, but in the search space of the algorithm. Okay, so we have the search space in the so in the search space of the algorithm, this is the search space, and we know that there are many infinite algorithms are there, A1, A2, like this. You may have many possible algorithms, and n contains to infinite. And we might have explored some search space. We are exhaustively, we are not able to explore complete search space. So people still believe that there may be some algorithms available which is still we need to explore, and using that algorithm we may be able to solve the problems in the deterministic, with the help of the deterministic algorithm that runs in the polynomial time. So people believe that in the search space there may be some unknown, some algorithm which is not yet discovered. There may be availability, and later on it may be available, and we will claim that okay, P is equal to NP. Or until you search the complete search space, you cannot claim that P is not equal to NP. So this is the relationship people commonly believe. we, we have the NP NP complete. So in NP complete and NP hard, we have the relation commonly believed relationship is like this. So people say that okay, this is the class NP problems. Okay, this is the NP. This is the NP group, and this is the class P problem. So this is the class P behavior. Then the commonly believed relationship is like this. People think that this is the NP hard group, NP hard, and this is this intersection is actually this is the NP complete. So this is the commonly believed relationship. This is people commonly know. So this is the commonly believed relationship. Okay. So among the P, NP, and NP, P, NP, NP complete, and NP hard, this is the relationship people are going to achieve. So see that we have the class P problem which has the deterministic algorithm that runs in the polynomial time. We have the class NP problem for which we have the non-deterministic algorithm that runs in the polynomial time. And NP complete is believed as some harder problem of NP. Means every NP complete problems is also the NP problems. So this is this area. This is the intersection of NP hard and NP complete, and in this is the these problems are somewhat harder as compared with the NP group, and they are known as the NP complete. Okay, so all NP complete problems are also the NP problems, but there are special characteristic in this NP complete problems. If you have the say you may have you have some NP complete problems L1, L2, L3, L4. So if these are the NP complete, you have the NP complete. If these are NP complete problems like this, you may have the Ln. If L1, L2, L3, L4, Ln, these are the NP complete problems, then we have the relationship on these problems. What relationship is there? We can solve the problems. Means we can solve, say we can solve L1 problems with the help of the algorithm available for the L3, or we can solve L3 with the help of the algorithm available for the L1. We can solve L2 with the help of the L3, or L3 can be solved with the help of the L2, and this is known as the reducibility. So there is a concept of reducibility. Reducibility means one problem reduces to the other problems. So like you can say you have the problem L1 and you have the problem L2. We can say that L1 reduces to L2. This means we have the algorithm for the L2. We have the algorithm for the L2. And what we are going to do, if L1 reduces to, we can say that L1 reduces to L2. And some books denote L1 reduces to L2 like this, or in Coreman they use the instead of this sign they use this sign. Okay. So what you mean by the L1 reduces to L2? This means you are solving the problem L1 with the help of the algorithm L2. And if you are able to do so, then you can say that L1 reduces to L2 means L1 can be solved with the help of the algorithm available for the L2. But see, you can think that L2, once you are going to solve the problem L2, this algorithm may take the input differently as compared with this algorithm. Say, input of this algorithm can be graph, and input of this algorithm can be a list. So what you need actually, how you can solve this problem with the help of this algorithm, where this algorithm requires input as the graph, and but input of this algorithm is a list. So what you need actually, you need to go for the transformation of the instance. So you need some algorithm, which can transform polynomially polynomial transformation. This means, see, this algorithm L1 takes some input in different manner, say for example list, and algorithm 2 takes the input in the form of the graph. So first you need to determine the algorithm which can convert the input of this algorithm L1 into the form of the input that L2 will take. It means this list can be converted to the graph. If L2 takes the input as the graph and input of this L1 is the list, then this list input must be converted into the graph. Then this algorithm will take the input, and the algorithm is written which takes the input as the graph. So you have the instance, means you have the input. This is the input of L1. So you need some polynomial time transformation, and this will become the I dash. And I dash is the input which algorithm 2 can take in the form of the algorithm 2. Once algorithm 2 is going to run, then algorithm 2 is going to produce the output, and say your algorithm 2 L2 can be produce the output in the form of the graph or list, whatever. But L1, say if it is going to produce the list output in the form of the list, like in input is a graph and your output can be the list, means matrix, then but output of this algorithm may not be the matrix. Output of this algorithm may be some kind of graph or something other. So what you need, this output is transformed into the output of L1. So you will come to know that what is the output of the algorithm L1. So this again you need some polynomial time transformation. So this algorithm polynomial time transformation means you have to determine the deterministic polynomial time algorithm which can transform the instance of L1 into the instance of L2. And also once it produces the output, you need to determine the deterministic polynomial time algorithm which can transform the output of algorithm L2 into the form of the output of the algorithm L1. So this, if you can do so, if you can find these two algorithms which runs in the deterministic polynomial time, then you can say that L1 reduces to L2. Remember that this must be deterministic polynomial time, and here also this must be deterministic polynomial time. So whenever you have found the deterministic polynomial time transformation of the input of L1 into the form of the L2, and whenever it produces the output, algorithm L2 produces the output, you have to write the deterministic polynomial time algorithm that can transform the output into the form of the output of the algorithm L1. Then you can say that problem L1 reduces to L2 means you are going to solve the problem L1 with the help of the L2. So this is the reducibility concept. And what people have found that the problem which are in the NP complete group, the problem which are NP complete, they have the characteristic that if you can solve one algorithms, then you can solve all algorithm. Means if you can solve any one NP complete algorithm, say these are the NP complete problems. These are the NP complete problems. And if you can solve any one NP complete problem, say L3, this is the L3, and if you can solve L3 in deterministic polynomial time, okay, if you can solve this L3 in the deterministic polynomial time, this means all NP complete problems can also be solved in the deterministic polynomial time with the help of this kind of reducibility. It means this is the NP and NP complete. NP complete are the some harder problem of the NP, and in this group you have the special characteristic that if you can solve one problem, then you can also solve the other problem. Means in this group, in NP complete group, those problems are in this group. They have the characteristic that they are reduces to every other problem. So that's why I'm going to tell you that if L1, L2, L3, L4, Ln, these are the problems in the NP complete, then we have the special characteristic in these problem that every problem reduces to every other problem. Means L1 can be solved with the help of L4, or L4 can be solved with the help of L1, L1 can be solved with the help of the L2, or L2 can be solved with the help of the L1, L4 can be solved with the help of the L3, and L3 can be solved with the help of the L4, or L3 can be solved with the help of L1, and Ln can be solved with the help. Means every problem reduces to every other problem. So that's why if you can find, you just need to determine the solution for one NP complete problem that runs in the deterministic polynomial time. In this way, you will be able to find the solution of every other NP complete problem because of this reducibility characteristic. So problems which are in the NP complete group, they have the special characteristic that every problem reduces to every other. So this means if you can find the algorithm for one problems, means you have the algorithm for other problems which runs in the deterministically polynomial time. And that's why actually we have the notion here, you have the notion here as the complete, this complete. So this complete means if you solve one, it means solve all. So that's why this is known as the NP complete. Here the notion is NP, and NP stands for the NP says that the problem first comes in the NP group. So this is the NP. So for being the NP complete, the problem must be in the NP, and complete refers that solve one problem means solve every other problems. So if you have just determined one deterministic polynomial time algorithm for any one NP complete problem, this means you can solve all other problems in the deterministic polynomial time because every problem reduces to every other. Whenever you go for the NP hard, the NP hard problems are more harder as compared with the NP complete. So here NP need not, you remember that NP, here NP stands for the non-deterministic polynomial time, here also non-deterministic polynomial time, but here NP does not mean non-deterministic polynomial time here. It says that it is harder than the NP complete. NP hard means the problem which are the NP hard means they are harder as compared with the NP complete, and this means the problem which are NP hard need not be in the NP complete. The problems can be here, problems can be here, problems can be here, and if problem is here, it is not in the NP, but this is the NP hard problems. These are the NP. So that's why these are the very hard problems as compared with the NP complete. So that's why NP hard says that these are the harder problem of the NP complete. So presently, whatever NP hard problems we have seen, whatever NP complete problems are there, they are also the NP hard problems. Okay, but there are the problem for which you may not write the algorithm or some optimization problem for which you don't have the non-deterministic polynomial time complexity will come in this area. So this is the notion. So if you can solve one NP hard problems, if you have the same, if you have the L1, L2, L3, these are the NP hard problems. And if you have the solution for one NP hard problem which runs in the deterministic polynomial time, then you may not be able to solve other NP hard problem in deterministic polynomial time, but you can solve every NP complete problems with the help of the deterministic polynomial time. Okay, because every NP complete problem can be reduced to the NP hard. So whenever you have the solution for NP hard problem, then you can also have the solution for the NP complete problem, but you don't think that you have the solution for other NP hard problems. No, the other NP hard problems which are here, you may not you may not be able to solve because NP hard problems are not reduced to other problems. This is the way. So this is the commonly believed relationship. People think that in our computer science we have the four computational classes. One is the P, NP, NP complete, NP hard. So problem P, first try to solve the problems which is which comes in the class P, and this is expected. We don't want to go for the exponential cases, and some harder problems we don't have the deterministic complexity, but we have the non-deterministic complexity that runs in the polynomial time. They are the NP problems. Some harder problem of NP comes in the NP complete. Okay, but in NP complete group, we have the special characteristic that if you can solve one problem, it means you are able to solve every other problems. So every problem reduces to every other, and in NP hard problems, you can say that if you can solve one problems, you can solve all other NP complete problems, but you may not be able to solve other NP hard problems. So this is the relationship among the NP complete and NP hard. Okay. So at the beginning, satisfiability problem was known as the NP hard at the beginning. This was the only problem which was known earlier as the NP hard problem, and with the help of the Stephen Cook. Around 1973, Stephen Cook has find out that okay, satisfiability problem is the NP hard, and he also find out that every NP problem reduces to the NP hard problem. And with the help of the reducibility, later on, people have find out many many problems which are the NP hard. So you can say that the problem L is NP hard. You can say problem L is NP hard. L is NP hard if and only if L reduces to the satisfiability. Sorry, uh, reverse. Satisfiability you can say satisfiability reduces to L. So at the beginning, with the help, Stephen Cook has proved that satisfiability problem is NP hard. So satisfiability problems, you know the satisfiability problem, whether it can be the circuit satisfiability or it can be the Boolean variable satisfiability. So you know that you have the circuit and you have the n inputs, and this circuit is consist of the logic gates and or nor whatever, and you have the output. From 1 to n you have the input, and you want to determine what is the possible assignments for this, for which circuit will give output 1. If circuit will give output 1, then you can say that okay, circuit is satisfiable. So this is the satisfiability problem. Or if you have the any Boolean formula which has true or false value, so you have the n variables whose value is true or false. You need to determine the value for the variables whether true or false, so that the formula is satisfiable. Formula gives the value true. If it gives the output true, it means it is the satisfiable. So this satisfiability problem is at the beginning was known as the NP-hard problem. So if you want to prove that L is NP hard or not, if somebody may ask you that problem L is NP hard or not. This is NP hard. You need to prove whether it is the NP hard or not. So what if for proving the problem whether it is the NP hard or not, what you need to do? you need to prove that satisfiability reduces to L. And Stephen Cook has proved that all NP problem reduces to the satisfiability problem. So once satisfiability reduces to the L, then L is also the NP hard. And if L belongs to, if this is true, if satisfiability problem reduces to L, then L is NP hard. And if L belongs to NP, if L belongs to NP, then L is also NP complete. Also NP complete. Okay. So this is the notion. Using this kind of concept, nowadays people have proved there are many problems. We have seen that they are the NP complete, like 0 1 knapsack problems in NP is NP complete and NP hard both. Okay, and Queen's problem, this is also NP complete. Traveling salesperson problem, this is the NP hard problem. And Hamiltonian cycle problem, this is also the NP hard problems. Node cover problem, this is also the NP hard problems. So there are vertex cover or node cover, they are the NP hard problems. And every NP hard problem, every NP complete problem, they are also NP complete. In presently, every NP complete problems are also NP hard. So this is the notion of actually NP complete, NP hard, and NP complete. So for this actually, so at home you just see the reducibility concept. There is one famous problem which is Clique problem. Clique. So what do you mean by the Clique? Actually, Clique is a graph. Clique is a graph. So like we have the graph. These are the vertices. We may we may have the graph. So Clique is a graph which is known as the maximal complete graph. Maximal complete graph. This is the maximal complete graph. And what do you mean by the maximal complete graph? Means every node is adjacent to every other node. This is the maximal, means there is a, between every pair of vertices you have the path. So you can say there is a path from here to here, there is a path from here to here, there is a path from here to here. The, means there is a path from here to here, there is a path from here to here, there is a path from this vertex to this vertex, and there is a path from here also. If you consider this, then there is a path from here to here, then from this vertex to this, this to this, and this to this. If you consider this vertex, then you have the path from here to here to here, and then also you should have the path from here to here, and from here to here. If you consider this, you have the path from here to here, and here to here, and here to here. If you consider this, you have the path from here to here to here to here. Means if this is the maximal complete graph and you have the n nodes, then every node has n minus 1 edges, incident edges. So you have the n minus 1 edges incident. Okay. If you, so this is the maximal complete graph, and this is the Clique. The maximal complete graph is a Clique. So what is the problem actually? We have the max Clique problem. We have the max Clique problem. Max Clique problem is to determine in the given graph what is the maximum size clique available in the graph or not. Like if you consider this graph, so this is the clique of size 5 because every node is adjacent to every other. If you can extend this graph like this, you may have the more nodes like this. Okay, and you can have the more nodes, and you have the edges like this. You may have the edges, no problem. Okay, you can have the edges. So this is the graph, and if you are given this graph, okay, and somebody asks you that what is the maximum size click available in this graph or not. So see, you need to determine, and you have the click of size 2, because there are, this is one node and this is one node, and there is a path from every other nodes. So this is the click of size 2. If you go for the 3, this node and this node and this node you can consider, then you come to know that from here to here there is a path, from here to here there is a path, from here to here there is a path. Means from this node you can go to this, you can go to this directly, from here also this and this. So this is the click of size 3, but your objective is to determine the maximum size click. You can see there are, whether maybe the more number of more maximum size click available or not. So 3, then you can say that 4, 1 2 3 and 4 you can see. So from here to here there is a path, but not, there is no path from here to here. But you consider if this group, this and this, so you can see that okay, this is the click of size 4 available, because there is a path from here to here, from here to here, from here to here. And if you consider this node, means every, this is the maximal connected graph having the 4 nodes. So till now you have found the click of size 4. Now you can go for the click of size 5. So you can add the node one by one. So this, and you can consider this. And you can say that okay, this is not the click of size 5. You can consider this. This is the node which has click ups, which is the 5 number of nodes. It is not also going, this is not the maximal complete graph. If you go for this is not the maximal complete graph. But if you can find this group, then you see that every node is adjacent to every other nodes, means there is a path from every node to every other node. And how many nodes are participating here? 5. So click of size 5 is available. Then you can verify whether click of size 6 is available or not, 7 is available or not. So the problem, max click problem is like this, and say that determining the click max click problem is NP hard problem, because you know that you have to you have to identify the all possible combinations in, okay, if you have the many much complex graph, then if somebody, even if somebody says that okay, decision problems, somebody may ask that okay, determine in the given graph whether the click of size k, say this is the graph, and somebody may ask you that okay, determine whether the click of size k available or not. For example, click of size 5 is there. So how you have to see all possible combination 1, 2, 3, 4, and 5. This group you can consider. Then 1, 2, 3, 4, and 5. This group also, this node you can consider. 1, 2, 3, 4, and 5. This can also consider 1, 2, 3, 4. All possible combination of 5 you need to come. And you know that in the complex graph, this kind of combination, if you have the n vertices and you need to find five group, and for the combination of the 5, it is exponential. So this is very large. So if you go for the brute force algorithm, there is no brute force algorithm available for the click, determining the click. This is the click decision problem. Click decision problem says that determine the click of size k or not. So which is known as the click decision problems. Okay. So you have the click decision problems. So in the click decision problem, you simply you will be given the graph, and you will be given the some k value, and you need to prove that, you need to decide whether the click of size k available or not. If yes, then you can output yes, otherwise you can say no. In max click problem, you are supposed to determine the maximum size click, not if you have determined the click of size 5, then you can also prove that click of size 6 is available or not, 7 is available or not. And if you have the n vertices, you need to determine whether the click of size n is available or not, click of size n1 n minus 1 is available or not, click of size n minus 2 is available, or and so on, like this. So even click decision problem is hard, and max click problem is naturally hard. So we don't have the deterministic polynomial time algorithm. This is the NP hard problem. So if you have the some Boolean variables like say x1, x2, and x3, okay, and you have say x1 bar, x2 bar, x3 bar. You have the variables like this, and these variables, there are some classes, in the, if you go for the formula, then you will have some classes like, you can, classes can be joined by the conjunction. This is the C1 and C2, or classes can be joined by the disjunction. So if you have the n variables, you need to determine that whether this formula is satisfiable or not. This formula is satisfiable then if this is true and this is also true. This class must be true. And if this class, if you can consider the class 1, then you may have the literal x1, x2 and x3, and within the class they will be joined by the or group, say x1 or x2 or x3, and then this is one class, and class can be joined by the conjunction. So this is the class 2, this is class 1, class 2. So say class 2, you have the x2 bar, okay, and x2 bar, or sorry, x1 bar, or x2 bar, or x3 bar. This may be the kind of formula. So if you have x1, x2, x3, this is the x3. So if you are given this formula, you can already ask that whether this formula is satisfiable or not. So if you know that this problem, then this satisfiability problem can be solved with the help of the Clique decision problem. Means CNF, conjunctive neuron form satisfiability, is reduces to the CDP. CDP means Clique decision problem, which is, this problem is known as CNF. So how you can have, that input of this CNF, conjunctive neuron form, this is the conjunctive neuron form class, because joined with the you want to determine whether this conjunctive neuron form formula is satisfiable or not, and if you write the algorithm, then your algorithm will take this list. But once you go for the quick decision problems, your algorithm will take this kind of graph. So first you need, if somebody say that CNF reduces to the CDP, then you need to prove that CNF, this can be how you need to show that there is an algorithm which can be used deterministically to transform this conjunctive neuron form formula into the form of the graph. So you can see in the books it is given. For conversion, actually, for conversion to the graph, people have written the literals in one class like this, x2 and x3. This is the literal in class 1. This is the literal in class 1. X3 is the literal in class 1. One denotes the one literal, like this. And then you have the class 2. So x1 bar is the literal in the class 2. x2 bar is the literal in the class, okay, in the class 2, and x x3 bar is the literal in the class 3. Now for defining the ages, people see that you cannot define the ages, which is the complement x1 and x1 complement. So you cannot have the age. You can go for the age like this. You can go for the age like this. x2 and x2 bar, you cannot have the age, but you can have the age from here to here. You can have the age from here to here. Now from here, x3 and x3 bar, you cannot have age, but you can have the age from here to here, and you can age from here to here. So this is the conversion. You have converted. So conversion, you know that it can be done in the deterministic polynomial time. You just determine the ages connectivity. Now how many formulas are there? There are two classes. So CDP, now you can give this graph as the input to the CDP algorithm. And CDP algorithm will determine the Clique of size, because you have the two classes, it will determine the Clique of size too. And you know that in this graph, We have the clique of 6 cliques of size 2. So this is one we have. Okay. So and this is the node, and this is node. This is one clique of size 2 because there are two vertices, and you know that this is the maximal connected graph. This is also a clique of size 2. This is also a clique of size 2. This is also a clique of size 2. This is also. So you don't require to determine all possible clique. If even you can find at least one clique of such the number of classes, say here 2, then we can say that yes, the clique of such 2 available, then you can report that yes, formula is satisfied. So this is the reducibility. You can see the algorithm at home. So that's all. From the class P, NP, NP complete, and NP hard. Okay, you need to study this thing, and you can explore either Coleman book, or you can go for the Shartaz Sahni book. You can find the details in both the books, and you just go through these books. You can see the max click problem. You can see some non-deterministic problems for the max click, and you can also see the non-deterministic algorithm for the 0-1 knapsack problems. Okay, and you see the conversion, how you can reduce the CNF conjunctive normal form formula, how you can solve this problem with the help of the click decision problem. So CNF satisfiability reduces to the CDP. People have proof. You can see the proof it book also. It is given in the books. You can see some other problems like vertex cover problems also, how they are working. Okay. So this is the brief about the P, NP, NP complete, and NP hard. For getting details, you can explore the chapters in much detail. Foreman has given the sufficient details for the P, NP, and NP complete. You can also find the details in the Sarta Sahni book, and other books are also there as a reference. You can take where you can find the discussion of the P, NP, and NP complete problems. Okay. So this is the portion you have to study as much you can do. So we very briefly we have covered. Just you need to. This is the overall notion, and then you for the study purpose there is a number of things you have to study. You can go for the Hamiltonian graph. You can see the how turbulent salesperson problem reduces to the Hamiltonian cycle problem. You see the hierarchy of the reducibility, and in the book you will find the detailed proof. Detailed proof is given in the Coleman book, where people have proved that how problems are reduced to the other problem. But in broadly, you see that in computer science we have the 4 classes of problems: P, NP, and NP complete, and NP hard. And any problems will come in any one of these groups. And if the problems are in the NP complete or NP hard, then really for such kind of problems you need to do the research to determine the efficient algorithm, and that algorithm should solve that problems in the reasonable time. Okay, because the nature of such problems are exponential in nature, and this is the task of computer engineer or computer scientist. If you are a computer scientist, then actually you need to find the solution of NP complete and NP hard problems. You are not supposed to find the solution of class P problems, because class P problems have been solved and we have the deterministic polynomial time algorithm, but you need to determine the algorithm that can solve the NP complete or NP hard problem much better as compared with the earlier one. You see the existing algorithms for the traveling salesperson problem. You may have the number of algorithms, and find out the way can you have some other algorithm which you can use to solve the more efficiently traveling salesperson problem. And for that you need to go for the algorithm design techniques, and whatever algorithm design technique you have studied, maybe the dynamic programming, branch and bound, backtracking, or greedy method, you may see that which design technique will be applicable for this kind of problem. If not, then you can find out some new design techniques, or you can mix up with some design technique. So true task of the computer scientist is to find the efficient solution of NP complete and NP hard problem, not for the class P problem. Okay, so these are the challenging problems. So we have the many problems. There are many problems you can find out in the books. There are many problems, well-known problems, which are very simple, but they are complex in the nature if input size increases. And we need to provide, like graph coloring problem is also one challenging problem, and you need to find out a way to solve this problem efficiently. And there may be possibility that after some times we may be able to execute the non-deterministic algorithm if we have some intelligent programming language in the next generation.